Okay, so going a little further with this analogy, I basically sort of set up, I sort of copied down the stuff I had from last time, and tried to sort of organize it. So in electrostatics, we think of like a plus or minus a negative charge, or sorry, a positive or negative charge. And in the vacuum cleaner analogy, that's like blowing and sucking hoses. The field lines we have in electrostatics are like the paths that air molecules take. The electric field then is like a field that shows the velocity of air everywhere. Okay, so and so obviously at any point in an air molecule's travel, the path it takes is going to be parallel to the velocity of air at that point, right? And so similarly, the field lines always run parallel to an electric field at some point. And then finally, we have the electric flux through a surface. And this is the idea we're going to explore here. What I want to start with is by telling you that it's analogous to the rate at which a volume of air flows through a window. So let me set up a situation where these two have equal positive and negative charges. I'm going to draw what the field lines sort of look like. Okay? They end up looking basically like this. Okay? And this one goes like that, and then we have that one's going to go off the panel. So what do I have? 8. Oh, I actually did it right. I've got 8 for the positive, 8 for the negative. And I'm just going to say there's equal charges here. Okay, so this is what these blue are what the field lines look like. Okay, but we can also think of this as being like blowing and sucking hose right next to each other, and this is how the air travels between them. Most of it gets sucked straight, a good bit of it gets sucked straight from the blower to the sucker, but some of the stuff from the blower goes off this way and maybe never gets back to the sucker. And then the sucker actually has to pull in some from outside to compensate for that. In reality, I think it actually all does go in eventually, but maybe the stuff that goes off this way has to take this big circuitous path around, okay? And that's how the electric field lines look around a positive and negative charge as well. We know this, okay? We've discussed this already. What I want to do now is say, take this idea of drawing a line around this further, but we're not just talking about a line because we're not really talking about two-dimensional space. We're talking about three-dimensional space. So instead of having a line, we'd imagine like a window or a surface that we want this stuff to go through. So this here, if we want to measure the electric flux through that surface, what we're doing is we're taking the electric field all along this surface, and we're sort of, in a sense, adding up all of the electric field along here. And that's a strange idea because, of course, you can measure the electric field at any point, and there's an infinite number of points here, right? So we could be talking about adding up an infinite number of vectors, right? Obviously, that's not what we're doing. But what I want you to think about it is, it's like the rate of airflow through a window. So imagine this green thing is like a window, and you're seeing all this from above. So the window extends, sort of into and out of the screen or whatever you're looking at this on. And so there's this window, and we're looking at the top of the window, and some of the air goes through this window, some doesn't. It's just like an empty window frame. And you assume, of course, that the actual frame bits are infinitely thin, so they don't actually impede the airflow. It's just this sort of phantom window that sits there. So we've got this flow here through this window, and so we want to talk about how much air flows through the window. What's the rate of air flowing through the window? Say the rate of airflow through the window per second. So what I'm going to do is we're going to come over here, and let's draw a situation where we have the air just flowing. Let me try to get some sort of like parallel straight lines, as parallel and straight as I can make them, which is obviously not terribly parallel and straight, okay? But here is the airflow, and let's say this airflow is uniform, so the velocity of the air everywhere is the same. So what I'm going to do is say these are like the flow lines we drew. These are like the field lines, and so now I'm going to draw in little arrows that show the velocity of the air, and you can draw these anywhere. The point is, in this little sample we're doing, they're all the same direction, all the same volume. So what I'm going to do is I'm going to say, let's say, where would I want to draw this? Velocity of the air is constant. Okay, so everywhere in this area, it's a constant velocity of the air. Later we'll talk about how to do it when it changes, but for now, let's just look at the constant velocity of the air. Now, here is a window, and we're drawing this window here. And let's say the window has actually a, so if we look at it sort of in 3 dimensions, it's like this. And let's say the window has a, I'm going to say this dimension, it's D, okay? So this here is that top we're looking down on. So like this is the top. Here's a view we're looking down from the top, but here's what we see here. Here's D, and here's H, okay? So it's got an area of D times H, okay? Fine. Now, the question is, in 1 second, let's say, how much volume of air flows through this window? So we're going to say, tell you what, I'm going to say V is capital V. I'm going to put little things on here to keep it different from the velocity, okay? This is a capital V, and that's the volume of air. Okay, the volume of air that flows through, and now I want to talk about the amount that flows through in some period of time, delta T. Okay, so delta V is the volume of air through the window in delta T time. Okay, so I think in order to facilitate this whole thing, I'm actually going to, my apologies here, let's see, we'll take that bit, and I'm just going to move that, crap, let's see, hold on. Okay, so let me grab it at the very, now it's unselected. Yes, watching me figure out how paint works. This is really how you want to be spending your time, isn't it? Okay, so now we're going to take that and shove that all the way to the bottom, just get out of the way from it. So this is the volume of air through a window in a delta T amount of time. And in fact, I'm going to get rid of this thing too. Okay. So now we want to figure out how to calculate that, given that we know, say, V and H and D. What else do we need to know? Well, we need to know the angle this window is at, right? So you can imagine here that you might be like measuring, like say this is perpendicular. So let's just say if the window is perpendicular, why does the size of the pen keep changing? It's bizarre. Okay, is perpendicular, and now this is too small. I want it like in the middle. Whatever. Okay, perpendicular to V, then, okay, then we can imagine then like the velocity coming through this way. Okay, there's your velocity, and I did them in purple before, so I apologize. Okay, if the window is perpendicular, then you can just see how you would have this window here, and the dimensions are like these, okay? And in delta T time, the air molecule that was here would have moved this far. The air molecule in this corner would have moved this far. This one would have moved like that. This one would have moved like that. And so all these little bits of air would have moved this far, and you'd have this cube here, not cube, but this volume here would be the amount of air that went through here. So here is our D, that's this dimension there. This is our H, and this length here is how far the air has moved in time delta T, and that is V delta T. Okay, so now in this case your delta V, or your delta V volume, so delta capital V, is going to be just the volume of this, right? Which is then D times H times delta T. No, I'm sorry, times V times delta T. And then if you want to get what we would call like a flow rate of volume, okay? So we just want to turn this into delta V over delta T, and that's equal to D times H times V, your speed, okay? So that's simple. Now if the window is not perpendicular, so let's say the window is, let me go back to the green color. No, actually, let me go to red, and then I can do something different. Okay, so let's say the window is at an angle like this, okay? Well, now, clearly you're not going to get the same amount through, because you're going to get, you're coming through sideways in the window, so, you know, less air comes through. But you can imagine, one way to look at this is you look at the cross section of air that coming through that gets there. And what you'll see is that, for example, here you'd get less than you do here. And if your window were completely parallel to the flow, you'd get none, right? So let me do that one in a different color just to keep it sort of perfectly clear. Let me do that one in, what's a good color? Brown, okay? So brown, clearly, the volume you get through is going to be 0. And the red, you think it's going to be bigger than 0, obviously, but less than this. So what I'm going to sort of submit to you for your approval in the next video, I think, is a formula we can actually use that accounts for basically this angle here between the airflow direction and the surface. So that'll be in the next video because I'm about out of time for this one.